We're going to continue our discussion of our chapter on chemical reactivity and mechanisms with this section here, section 6.7, which reviews a certain type of reaction called polar reactions, which would involve ions as either reactants, intermediates, or products. We'll see for the most part that they exist as intermediates, these ions. And let's define these terms. So we have here electrophiles, and we have this term here, nucleophiles. So what exactly do they mean? Let's break down these words here. So they both contain the word or the suffix here of phile. So this means that they loves, right? So both nucleophiles and electrophiles love something, but they love something different. A nucleophile is, in general, a negatively charged species, and it's sometimes abbreviated NU, and that is seeking out a positive charge or a nucleus, which is positive. And an electrophile, we'll see that that's sometimes abbreviated with this E plus symbol, and that's looking for electrons or a negative charge. So we know that negative charges are attracted to positive charges, and that's the whole premise behind these nucleophilic and electrophilic reactions. Again, with a nucleophile, we have sometimes a formal negative charge species, and they are electron rich. So they are able to, we'll see in the next slide, donate electrons, whereas our electrophiles are generally electron deficient or able to accept an electron pair. So we see in our examples down here that we have this methyl chloride molecule, and chlorine is very electronegative, so it's what we call an electron withdrawing group. So because of that electron withdrawing group, the electron density is shifted towards the chlorine, and that results in a partial positive charge, so a delta plus on this carbon atom here. And this is considered an electrophilic center, right? Since it's partially positive, it's looking to find some electrons to fulfill, it's attracted to electrons because it's positively charged. And then over here, we have our other example, our methyl lithium. And again, due to induction, carbon being more electronegative than lithium, carbon is stealing that electron density or creating a higher electron density than the lithium. So it's becoming a partial negative charge on that carbon now instead of a positive. And this would then be considered the site of, or a nucleophilic site on our carbon. So induction can create either electrophilic or nucleophilic centers, and we'll look at some other cases of both. So let's start with our nucleophile. So nucleophile, again, is looking for a positive charge because it is an electron-rich species, and it's able to donate a pair of electrons. So in the past, in chapter 3, we looked at Lewis acid and Lewis base reactions, and nucleophiles would be considered Lewis bases because they are able to donate a pair of electrons. Also, the more polarizable, right? So the more easily the electron cloud can be distorted, the stronger the nucleophile can be. So in our first case, we look at our methyl lithium molecule over here. And again, through induction, this partial negative charge is created on our carbon, and that will be our nucleophilic site there. In the second molecule, our ethoxide, this is in general just called an alkoxide, right? If it's not ethoxide, methoxide, etc., they're all alkoxides. And this has a formal -1 charge on the oxygen. It's maybe a deprotonated ethanol that results in this formal negative charge on the oxygen, and that there would serve as our nucleophilic site. Then we also have ethanol here, which these lone pairs on the oxygen do not have a formal negative charge, but they still can serve as a weak nucleophile. So this is our nucleophilic site here. And then our area of high electron density in this alkene would be our pi bond. So a pi bond can act as a nucleophilic center as well. So some examples of electrophiles we see here. Again, an electrophile is an electron deficient species. So it is able to accept a pair of electrons. So when we're considering if something has a positive formal charge, to be an electrophile, it must also be able to accept a pair of electrons. And these electrophiles, again, we saw in chapter 3, can act as Lewis acids. So some examples given down here would be a carbocation, which we see in the middle here. This has a formal charge, +1 formal charge on our carbon. So that is an electrophilic center, right, at that carbon there. We also have in this example with the chlorine again is a electron withdrawing group because it's much more electronegative than our carbon atom that it's bonded to. This results in electron density distortion and then a partial positive charge on this carbon that I just circled there, and that would be our electrophilic center. So they have on the side here this drawing of our carbocation, and if you recall, when a carbon only needs to have 3 hybrid orbitals, it would be sp2 hybridized, and its shape would be trigonal planar. That will become important in our next chapter, but what you also see is that it has this unhybridized p orbital, and that's why that carbon with the positive charge is able to accept a pair of electrons. So let's put all of our knowledge now of nucleophiles and electrophiles to work. So we'll start with our electrophiles, right? So they're looking for a nucleus, right? They are electron deficient, and we can see some examples given down here. This isn't a complete list. There's a better table in your textbook provided with a more extensive list of electrophiles, but we should be able to use this to get through what we need to with this molecule. So it asks us to list all the nucleophilic and electrophilic sites. So we'll start with the electrophilic sites here. So we can see wherever there is induction, that's a possible electrophilic site due to inductive effects. So here, where I'm circling, could result in a partial positive charge because of the electronegative oxygen there. And also due to resonance. So we looked at how these bonded pairs could form a lone pair on this oxygen. Either way, you look at it either through the inductive effect or through resonance. This site here would be an electrophilic center. You may want to, I'll draw an arrow to this oxygen here. You may want to consider that as an electrophilic center as well, because it's positive. So you're thinking that it's going to attract some electrons, some negative charge to itself. But the oxygen is not electron deficient, even though it has a formal charge. So it would not be an electrophilic center and able to accept a lone pair. So that's our one example for this molecule of an electrophilic center. And then we have a few nucleophilic sites here. So our first nucleophilic site could be the lone pairs on this alcohol functional group. So over here, this could be considered a nucleophilic center. So that would be lone pairs, right? Our nucleophile table down here. Also, we have this site here with these lone pairs on the oxygen. That could be a nucleophilic site. We have this alkoxide site here with 3 lone pairs. So that's another site of electron density. And what else do we have? We have a pi bond here. So this is also a site of higher electron density. So we see in this molecule, we have quite a few sites of nucleophilic centers, and we have that one electrophilic center. So we'll continue our next section with our next video lecture.